Today we are going to revise the first out of the two optics chapters that you have, and that is ray optics and optical instruments. And in the first part we talk about ray optics. Now ray is defined as the straight line path. Ray is defined as straight line path which the light takes, but here we make an assumption. And what is that assumption? The assumption is that the wavelength of the light is very much smaller than the dimensions or the size of the object. We have seen in the next chapter that if the wavelength and the size of the object, if they are comparable, if they are of the same order of magnitude, then light does not travel or is not seen, is not observed to travel in straight line paths, and it bends, and well, we call it diffraction. We call it diffraction. But we are not going to study this in this chapter, rather we did not study it here. Okay, so we will now revise ray optics. The other name of ray optics, what is it? Can I tell you? The other name of ray optics is geometric optics. The other name is geometric optics because we know in the derivations of the mirror equation, lens maker's formula, thin lens formula, and even the formula for optical instruments, we heavily use the geometry, the planar geometry of triangles, the linear approximations, sine theta equal to theta, tan theta equal to theta, and so on. Okay, so with that we will start our revision. First part is laws of reflection of light. Pretty simple. The incident ray, the normal to the surface of incidence, okay, normal to the surface of incidence, and the reflected ray, they are coplanar. They are coplanar. And what is the other law of reflection? The angle of incidence, which is the angle between the incident ray and the normal to the surface, that is this angle. Let's call it I. This is the same as the angle of reflection. It's this angle, let's call it R. You have studied these in school, but this is just a quick revision. Okay, so these are the laws of reflection. And mind you, okay, one thing which I would like to note here, these laws not only apply to flat reflecting surfaces, but they also apply to curved reflecting surfaces. Applicable to flat as well as curved reflecting surfaces. Because we make use of this fact later when we study refraction at a spherical surface, which is again a special type of a curved surface, right? Okay. The sign convention, what is it? Sign convention is used or is useful in solving problems, and this is a sign convention to measure the distances or to measure lengths. Now when I say lengths, please note that these are not actual lengths, but these are distances. So directed distances. Okay, let me put it in that way. These are directed distances. And directed distances, we know in coordinate geometry, we use them as coordinates. Directed distances can be 0, can be positive, or they can also be negative. So the convention that we develop here for a mirror, these conventions will also work. They are also used in analysis of lenses. Okay, so what are the conventions? The first convention is that all distances are measured from the geometric center of the mirror. All distances are measured or to be measured from the pole of the mirror. Okay, or optical center of the lens if it is a lens problem. Distances measured vertically upwards are positive, vertically downwards are negative. So this is very much like y coordinates sign convention, when they are positive and when they are negative. And the third thing is that distance is measured in the direction of the incident light, and it is always taken from left to right. Okay, we always place our object in front of the mirror and it is always to the left. So distances measured in this direction are positive and distances measured in this direction are negative. Because we always place object to the left of the mirror, the object distance u will always be negative. Is that clear? The object distance is always negative because we always place the object somewhere here. So this will be our u, if that arrow itself is an object. Is that clear? Okay. Then, what is meant by focus of a concave mirror or of a convex mirror? Focus is that point where the rays coming parallel to the principal axis, they are incident on the mirror, and post reflection they appear to converge in the case of a convex mirror, and they actually converge in the case of a concave mirror. That point is called as a focus. And if, okay, so in this case, what is the assumption? We are assuming that the rays are paraxial. Okay, what is meant by paraxial rays? The rays are parallel, and if they are not along the principal axis of the mirror, then in that case the angle which those rays or that beam of rays makes with the principal axis is very small. Okay, and the beam is incident very near to the, okay, to the center of the mirror. So that is the point. Okay, so this is called as the focus. Okay, now suppose you imagine a ray of light or a beam of light, sorry, a beam of light which is not parallel or which is not along the principal axis CP. Okay, in that case the point of convergence will not be on the principal axis, but it will be somewhere in a plane, and that plane is called as the focal plane. That plane is called as the focal plane. In diffraction, okay, in diffraction we require the focal plane, especially in studying what we call Fraunhofer diffraction. Okay, in Fraunhofer diffraction, what do we have? In Fraunhofer diffraction, the object, the screen and the light source, they are two, I mean, very far from each other. So to get the diffraction pattern, we actually put a lens there. Okay, we put a lens there. So the ideas of focal plane, they apply to both mirrors and lenses. That plane where a parallel beam of light after undergoing reflection or refraction is incident, okay, or is convergent. That particular point is called as focus. For a convex lens, for a concave mirror, the focal point is real. In this case, it is virtual because the rays do not actually meet there, because they will undergo reflection right here, but they'll appear to converge at this particular point, and that is the focus. So if the rays are actually intersecting each other, then the image formed is a real image. If they appear to meet at a point, then we call that image as a virtual image. The mathematical relationship which connects the radius of curvature of the mirror and the focal length of the mirror is f is equal to r upon 2. What is r here? R is the radius of curvature of this surface. R is the radius of curvature of this surface. This is r. And the focal length is the distance between the focus and the pole of the mirror. In this case, this will be r. Okay, this will be R and this will be the focal length. So PF is the focal length. Okay, fine. We next go to the mirror equation. The purpose of the mirror equation is to locate the image and also to obtain the magnification if we know its focal length and if we know where you have placed the object. So let me write down the notation here, the usual notation. U is the object distance to be substituted in the formula following the sign convention, and we know that U is always negative because we place the object always to the left of the mirror and the pole acts as the origin. V is the image distance. V is the image distance. F is the focal length, distance between the focus and the pole. Then M is the magnification. In this case we talk about linear magnification. What is meant by linear magnification? By linear magnification we mean the ratio of heights of the image and the object. Because we take the ratio of lengths, it is linear. If we take the ratio of the angles subtended by the object and the image, then that becomes angular magnification, which is important in the case of telescopes. So H prime here is the image height, H prime is the image height, and H is the object height. Using geometrical optics, using geometry you can prove that H prime upon H is negative V by U. We have proved it in our regular lectures if you remember. Just let me go back to this figure. U is the object distance, V is the image distance, F is the focal length of the mirror, distance PF, and this is H and this is H prime. AB is H and B prime A prime is H prime. Have you understood this equation, what it tells us, and the magnification formula?
Angular magnification क्या है इसका?
Okay, so linear magnification is the ratio of lengths and the angular magnification is the ratio of angle. Suppose you look at a distant star. Of course you are not interested right now in the radius or diameter of the star, and then suppose that star is subtending some angle at your eyes, some angle at your eyes. So this is called as the angle subtended by the object. Now suppose you, instead of observing the star directly through your eyes, suppose you observe its image under a telescope, and in that case the angle subtended by the image, not the object, the angle subtended by the image here this angle is beta. So this point is your eye. This is unaided, this is through telescope. So the ratio of beta and alpha is called angular magnification. Got it now?
How?
This is angular magnification. Alright.
So इथे normal lenses आणि mirrors मध्ये angular magnification येतच नाही का?
No, you can determine it, but your focus is more on viewing the interior of the object. So angular magnification is less relevant. What's more relevant is the linear magnification. Whereas if you're talking about two distant objects, then we have indirect ways to determine the temperature and other things like what exactly is happening there and so on. So we are just happy with even obtaining a very tiny image, right? Because see, now if for example take moon for example, what is the actual size of the moon? Well, it's very large. Okay, its radius is of the order of some 100 kilometers, correct? But if you look at it with your naked eyes or even with your telescope, through telescope, you will not see its image, let's say, whose radius is 1 kilometer. So you cannot say that you are gaining any magnification here because the the object itself is so big, that its image is always going to be smaller. So there the angular magnification is more relevant. Got it? Yes. Yes. Okay. Cool. Let's now go to laws of refraction. First law is very simple. The incident ray, the refracted ray, and normal, they are coplanar. So I'll not write the statement now. Incident ray, the normal, and the refracted ray, they are coplanar. That is our first law of refraction. Please remember this. Whenever any beam of light or any ray of light is incident on a transparent medium, a part of it is bound to get reflected. That is why sometimes we get to see the images, even images in the glass or in the window panes, isn't it? We know that it is transparent, but then why do we get to see the images? That's because of the reflection. Okay, that's because of the reflection. But for mirrors, it is only reflection. There is very little absorption, and we totally ignore it. All right, and we have this Brewster's law, which tells us that uh, the reflected ray is actually polarized. Okay, it is polarized at a particular angle, but that is a topic of separate discussion. We'll not bring that here. Okay, what is the second law of refraction? Also called as Snell's law. Snell's law tells us that for a given pair of optically transparent media, let's say media 1 and media 2, or medium 1 and medium 2, the ratio of sine of the angle of incidence to sine of the angle of refraction is same, and that ratio is called as the refractive index. N21 means refractive index of medium 2 with respect to medium 1. Refractive index of medium 2 with respect to medium 1. Now, so this basically tells us that the light enters 2. Okay, light enters medium 2, but before that it is actually traveling in medium 1. Now if you have two pairs of media, let's say medium 1 medium 2 and then medium 2 medium 3, in that case, if you want to define refractive index of medium 1 with respect to 3, then you can do that in this way: n12 into n23. This not only applies to two pairs, this also applies to 3 pairs, 4 pairs, or in general n pairs. So 1 3, so 1 2 and then 2 3. You can prove this, but we are not going to prove that. Is that clear, this formula n13? Okay, remember the subscripts. Okay, now continuing our discussion which we carried forward here, which we discussed there, continuing it here, we observe this lateral shift. I'm not going to discuss that because you already know it. In school you have seen that if you take a rectangular paperweight box like and if you look at some object through that, then it appears to be shifted. That shift is called as lateral shift. The emergent ray and the incident ray, they are parallel to each other, but they appear to be shifted using geometry and using formulae, let us say, of equations of lines. Distance between two parallel lines, you can easily determine the lateral shift if you know the dimensions of the box. In the textbook they have not mentioned any mathematical formula here, so I'm not covering that here. Okay, but note that R1 and R2 will be equal and I1 and R2 will be equal to begin with. Got it? Okay, next, apparent depth. This is a very common observation that if you look at bottom of a fish tank, let us say, it appears to be raised. The approximate formula for finding the apparent depth is given by the actual depth h real divided by n21, and generally n21 is always greater than 1, correct, because the medium 1 is air whose refractive index is 1, very close to 1. So the apparent depth is always smaller than the real depth, and this is the figure explaining that. Our eyes always perceive light to be traveling in the straight line, and this is also evident in the phenomena like uh, earlier sunrise and delayed sunset. Okay, all right. So that's apparent depth. Let's go to total internal reflection. The phenomenon of total internal reflection is observed only when light is traveling only when light is traveling from an optically denser medium to an optically rarer medium. Two points. First point is that being optically denser does not mean that necessarily it should be heavier, like its density, the mass density is greater. Okay, that's first point. Point number two, even when such a situation exists, light is traveling from an optically denser medium to optically rarer medium, that the phenomenon of total internal reflection will be observed only when your angle of incidence is greater than a particular value. Okay, so why is that? We can see that from this figure. Let us consider a ray emerging from A. Okay, let's say it is incident at this point. The angle of incidence is A01N. Okay, and you can see here that okay, but angle of reflection, sorry, angle of reflection is NO1C. That's not relevant now. We need to focus on the angle of refraction. So it is BO1, and let us say Y1. BO1 Y1 is the angle of refraction. Now farther you go, well, you're still on the surface, but farther you go away from A, you can see that this angle of refraction will be increasing, is found to increase, right? So if you consider now a ray of light emerging from A and incident at O2, okay, incident at O2, the angle of refraction, what will it be? It will be B2 O2 Y2, and clearly R prime is greater than R. R prime is greater than R, correct? So you can expect that this cannot definitely continue to go on forever. There will be some angle where the ray of light, the refracted ray of light will be almost parallel. Okay, assuming that the surface is calm, there are no ripples there, it will be traveling along the surface of the water. This angle is called as the critical angle of incidence, IC, and in such cases the angle of refraction is 90. In this case the angle of refraction is 90, so it is actually n1 sin IC is equal to n2 sin pi by 2, or sin 90 degrees. Because sin of 90 degrees is 1, the formula for total internal reflection is n1 sin IC is equal to n2. And when the angle of incidence is greater than this critical angle of incidence IC, you get to see the total internal reflection, and in that case you cannot apply the Snell's law because there is no refraction. Is that clear? So what is total internal reflection? The incident beam, if making an angle greater than the critical angle of incidence, will not emerge out, will not undergo refraction, but it will undergo an internal reflection, and it is total. No energy is being spent in the refracted ray because there is no such ray, and hence we call it total internal reflection. Using this phenomenon of total internal reflection, we can explain why diamonds shine, and also the phenomenon of rainbows. Okay, the phenomenon of rainbows. Alright, next let's now move on to lenses. The first formula that we have derived is the refraction at a spherical surface. So we assume that the the medium, okay, is inside. Okay, so inside this arc that you see, it is actually a spherical surface. It can either be a surface of a ball, a transparent light ball, sorry, glass ball, or it can also be a conical like shape like a cone. Okay, fine. So here we are again making that approximation that this is smooth. What does that approximation do? Assuming that this curved surface is smooth, if we sufficiently zoom in, if you remember we have seen this in our regular lectures, then what will happen? It will behave as if it were a flat surface. Okay, as if it were a flat surface. Anyways, okay. So what's the main conclusion here? What's the main conclusion here? The main conclusion is that if our ray of light is traveling from O, let's say it is our object, it will undergo refraction here. Okay, it will undergo refraction here, and it will follow obviously the laws of refraction. Sin A, n1 sin A is equal to n2 sin A, and let us say the image formed is here. So here V will be positive and U will be negative because all the distances will now be measured from the optical center, that is that. Okay, so U is positive, U is negative, and V is positive. What formula do we get? R is the radius of curvature of this surface. So the formula is n2 by v minus n1 upon u is equal to n2 minus n1 upon r. If medium 1 is air, then n1 becomes equal to 1. Okay, this is refraction at a single spherical surface. When you consider the image that you get here in this case, and now if you imagine that only this image is present and nothing else is present, and if you now imagine its image formation under another curved surface which looks like this, then you can apply the same formula one more time to get the position of the actual image of the object O through a thin lens. Not going to show that here. We are directly going towards the formula. Okay, so there are two important formula here. The first one is the lens maker's formula, and the second one is thin lens formula. What is lens maker's formula? The lens maker's formula has been derived. The lens maker's formula has been derived by successively applying this formula twice. Once we can already see that being applied here, and the second one, which I was explaining earlier, you forget everything but you just focus on image formed by this refraction. Okay, and now this image acts as an object for a spherical surface like this, and wherever that image is formed of this image under that spherical surface, that is actually the true image of it. Correct? And the lens maker's formula tells us that the focal length of the lens is given by n2 by n1 minus 1 into 1 upon r1 minus 1 upon r2. It is essential to note here what r1 and r2 actually represent. Okay, see, they are radii of curvature, but what is r1 and what is r2, it's easy to remember that. Okay, you imagine this surface first, this curved surface first, so this becomes r1. Okay, so this is r1, and then obviously the next one will become r2. Okay, is that clear? Okay, and also you have to focus on the sign convention. So even if r1 and r2 are in magnitude equal, their signs will be opposite. Okay, their signs will be opposite. Next, the thin lens formula. The thin lens formula is a mirror-like formula. In the mirror equation, we have 1 upon v plus 1 upon u equal to 1 upon f. For lens, it is 1 upon v minus 1 upon u equal to 1 upon f. And the magnification that you get, same notation, h prime upon h. It is v by u for thin lens. For mirrors, if you remember, it is negative of v by u, but for thin lens it is positive v by, or just v by u. Okay, just v by u. The convention that we followed there, the sign convention, it still applies to thin lens as well, or lens extensions. Alright, next is the power of lens. What is power of lens? Power of lens is a measure of convergence or divergence. Convergence or divergence of a parallel beam of light by a mirror, by a lens. Parallel beam of light by a lens. So if it converges closer to the actual lens, you will say that its converging power is more, its power will be more. And how do we measure it? Closer the focus is to the center of the lens, smaller the focal length. So we actually define the power of lens as tan of the angle delta, where delta is the deviation angle. Delta is the deviation angle, because when any ray emerges out of a lens, it is actually undergoing, or it has undergone, two refractions, one at this surface, the other one at that surface. But we generally don't show those minute details. We assume that this ray travels straight in a straight line till this section, and then it refracts that. Okay, so it is tan of delta, and to define the power of a lens, we take this h to be 1 unit. H is taken as 1 unit, and therefore it becomes 1 upon f. Please remember that diopter, the SI unit of power, diopter, is not having dimensions of L raised to minus 1. Okay, power of a lens is actually a dimensionless quantity. Why is that? That's because it is ratio of two lengths. Although we say that focal length is present in the denominator, you need to understand that this number h here, because we numerically take it equal to 1, we're not considering its unit. Okay, but actually it is one, let's say 1 meter upon focal length in meters, so the power will be a dimensionless quantity, just like a radian. Okay, radian is a unit, but it is measure of length of arc to the radius, right? Length of arc to the radius. So yeah, just like that, you have to follow this. Okay, power of lens. Now let us go to combination of lenses. Let's go to combination of lenses. Thin lenses in series. Two important formulae. Uh, if we want to replace this combination of lenses by one single lens, what will be the effective focal length? The effective focal length can be obtained by using a formula that we use for finding equivalent resistance of a parallel combination. So you have to take the reciprocals of all the focal lengths, you have to add them, and then whatever answer you get, you have to again take the reciprocal of that. So 1 upon f is summation 1 upon fj as j goes from 1 to n if you have n lenses kept one after the other. What about magnifications? The net magnification or the effective magnification is the product of the individual magnifications. So this sigma corresponds to sum, this sigma corresponds to sum, this pi corresponds to product. So powers get added and magnifications get multiplied. Refraction through prism. So we assume a triangular prism here. Let PQ be the incident ray. Now please note that the angle of incidence here is to be measured with respect to a line which is normal to the face AB of the prism. Then it will undergo refraction here at Q, and then when it emerges out at R, it will undergo another refraction, very much like lens. But in lenses, the surfaces are curved, but for a prism, these faces are flat. Okay, so this emergent ray, the angle of emergence, this E here, is to be measured with reference to a normal to the surface AC of the prism. Correct? This A angle, this is called as angle of prism. This is called as angle of prism. And then when this angle of prism is extremely small, okay, then you get a thin prism. And when you join two thin prisms together, you get something which you call a biprism, which is useful in obtaining coherent sources. Okay, is useful in obtaining coherent sources from just one single source of light, and that prism is called as a biprism. Call it Fresnel biprism. When you have two thin prisms, when you attach them, when you join them like this, so this is one thin prism, this is another thin prism, you join them like this, then you get something which you call a biprism. And you have to keep the source of light here, monochromatic source of light here, and then it is going to produce two virtual sources due to reflection and refraction, and then these two coherent sources will show the interference pattern. Anyways, okay, so what are the important relations associated with prism? First one is the angle of deviation delta. Angle of deviation delta. Angle of deviation basically tells us the angle between the direction of the incident ray and the direction of the emergent ray. So you can see that here. PQ has been extended to M, and SR has been stretched backwards to M, and that angle is our angle of deviation delta. Now in the textbook they have given a graph. Okay, they have given a graph of the angle of incidence and the angle of deviation, and that graph has a U-like structure, inverted U. Structure like this. Okay, so at this point where the angle of deviation is minimum, the angle of incidence becomes equal to angle of emergence. Okay, and then you can follow a mathematical procedure to finally arrive at an expression which connects the refractive index of the material of the prism with respect to, let's say, air or water, anything. Okay, depends on what in what material we are going to put that prism. Okay, so N21, the formula is sine of a plus dm by 2 divided by sine of a by 2. There are two angles here. First one is the angle of prism, which is not going to change no matter where you put that prism, in glycerine, in water, or you just keep it in air. Okay, but dm can be different. Okay, dm can be different, and that is how N21 will change. Okay, now if you assume that the angles A and DM are very small, then you can use the linearization. That is, you can approximate sine theta by theta. So sine of A plus dm by 2 can be approximated as just A plus dm by 2, and sine of A by 2 can be approximated as A by 2. If you continue to simplify that, you finally arrive at this expression for the angle of minimum deviation, which is N21 minus 1 into the angle of prism, that is A. So this relates angle of minimum deviation, angle of prism, and the refractive index of the material of the prism, assuming that the angles A and DM are very small. Alright, now let us quickly discuss optical instruments. The first optical instrument is called simple microscope. A simple microscope, its working is very simple. You can adjust the position of the lens, and you actually might have used it. Okay, if you have a lens at your home, you can see, and let's say you are reading a newspaper, then you can clearly see how the letters look magnified if you move the lens closer to the paper, and if you can actually study the patterns. Okay, sometimes you get a blurry image but magnified, you get a sharp image but its magnification is not that much. So usually the magnification, the simple microscope works well when you have magnifications, linear magnifications of, well, let's say somewhere in between 2 and 9. Correct? Okay. Now there are two possibilities here. This distance d is called as near point. And if you have placed your object at 25 centimeters from unaided normal eyes, then you can clearly see the image or the object. Can either be object or image. Okay. So if you form your image at this particular distance, so if v is equal to d, then you get the magnification which is given by 1 plus d upon f, where d is 25 centimeters. But the problem with this is you are still required to strain your eyes. You are still required to strain your eyes in that case. So you say, okay, I don't want to strain my eyes. I'm okay to compromise on the magnification. So if the image that is formed, okay, if you take this image at infinity, you know that if you keep your object at focus, the image formed will be at infinity, the virtual image, right? So in that case, the magnification becomes d by f. So it is 1 less than what it is if you get your image, okay, right at the near point, correct? So two magnifications, don't think that there are two images here. It all depends on where the image is formed, okay, where the image is formed. If the image is formed at the near point, then you have to strain your eyes a bit to see it clearly. So we compromise on magnification, we make it smaller. I mean, we make it smaller by 1, but then the well, the experience is more comfortable, okay, comfortable viewing, comfortable. So what is a compound microscope? In a compound microscope, there are two lenses. First one is called as objective, and the second one is called as eyepiece. The object to be viewed under a microscope, its image is first formed uh, by the objective, and the image that the objective forms acts as an object for the eyepiece, okay, which has generally larger focal length, okay, and the image that is formed by eyepiece, this is very similar to simple microscope. This is very similar as in the working, very similar to simple microscope. Okay, so what are the important formulae here? The first formula is the magnification achieved by the objective lens. Magnification achieved by the objective lens. It is given by MO equal to L upon FO. FO is the focal length of the objective lens, and L is called as the tube length. L is called as the tube length, and it is basically the distance between the foci of the objective and the eyepiece. Okay, so this is the focus of objective FO, and this is the focus of eyepiece B plane. So the distance between FO and FE is called as the tube length. Okay. Okay. Now again, as I said, the image that the eyepiece forms, it's very similar to that of simple microscope as far as the working is concerned. So if you form your image, okay, if you form the image at the near point, that's at B, then the magnification of eyepiece will be 1 plus d upon fe. If you form this image at infinity, then the magnification will be 1 less than that, but nonetheless the viewing will be more comfortable. And what is the net magnification in this case? For net magnification, you recall that these are lenses in series, so it will be MO into ME. What is MO? L upon F naught. What is ME? Okay, it is either 1 plus d upon Fe or simply d upon Fe. Is that clear? So this is the net magnification. Usually this net magnification is much greater than what it is for a simple microscope, right? In your book there is an example where they say the magnification is somewhere around 250, right?
Oh, I have solved it.
Yeah, it's there in the text.
Oh,
Yes, they have picked some values here and put all right.
okay.
Yes, okay. Last optical instrument, telescope. So in discussing telescopes, it is to be noted that we talk about angular magnification. We've already discussed it because you had raised it out there, but okay, let's revisit it. Just like a microscope, a telescope also has two lenses. The one is objective and the other one is eyepiece, but there is one difference. Objective's focal length in the case of a telescope is much greater than that of eyepiece, whereas for a microscope it's the opposite. Whereas for a microscope it is opposite. Okay, it is opposite. So Fe and FO is smaller than Fe. In this case, FO is greater than Fe. So the object is at infinity, obviously, because we are viewing stars or distant planets. The angle that the object is subtending at the objective lens or even at the eye is called as alpha. Notation wise, alpha is the angle subtended by the object at the lens. Now it doesn't really matter whether it is the objective lens or the eye. We know that it is going to be very small. And if we could zoom in, if we could magnify this, our job will be done. Correct? Okay, so what is beta here? Beta is the angle subtended by the image. Beta is the angle subtended by the image at the eye. So this is now called angular magnification because we take the ratio of angles. So this is angular magnification, beta by alpha. It can be proved that beta upon alpha magnification, by making some approximations, it is FO upon FE, where FO is the objective length of the focal length of the objective lens and FE is the focal length of the eyepiece. Okay, and in this case the tube length is the addition of the focal lengths of the objective and the eyepiece, because the image that is formed, okay, to get the better focus, the image that is formed of the star by the objective lens is at its focus, and we also adjust the position of the eyepiece so that its focus is also coinciding with that of the object. Okay, so in the case of telescopes it is angular magnification. So if alpha is, let us say, in seconds, not time. Okay, what is a second? 1 second is 1000, so 1 upon 3600 part of a degree. Okay, angle. So second is a unit, a much smaller unit of angle, and beta can then be, let us say, a degree or so. Or even if you take half a degree, you can clearly see how large the magnification is going to be. But remember, it is not linear magnification, but it is angular magnification. Alright. Okay, so that ends our revision of ray optics and optical instruments.